free to sit down and take just sign in. Thank you. Get you to sign in. Give folks another minute or two and we get started. Now there's a couple other people that were saying they're going to show up. So. Just like a class, no one's sitting up front row.
Buddy.
Alright, so I think most everyone's signed in. If not, you guys could just pass the sheet around. Let's just go ahead and get started. Hopefully I've got it all set up correctly so that anyone that's coming online, they can hear and see what we're doing. So my name is James. I'm a CHEM grad student. I work at the ARC. I've seen a few of you, so that's encouraging. Okay, as far as tonight's concerned, I'll be doing some examples, going over some of the main topics. As far as the actual exam itself is concerned, I can't really answer any questions about what's going to be on the exam or any of that because I don't know. Okay, you guys have a better idea about that sort of stuff than I would. I know the content, I know how to do the chemistry, and that's what I can show you. I've taught this stuff for like 5 years, so I've got a pretty good handle on how best to approach it. Okay. So if you guys have questions while we're going through something, just stop, and say, hey, I got a question. Otherwise, I know there's a few things that some people wanted to go over. Right now, I'm going to start with acids and bases, okay, chapter 5. Talk a little about what they are, definitions, that sort of thing. Go through, I got a hefty example problem, okay, and then we'll just kind of go on from there, okay? As we start a chapter, why don't you guys just open it up. If there's anything you guys specifically want to talk about, okay, we can talk about that stuff first, okay, and then if we have time, we can go through. I've got lots and lots of examples, okay? So, why don't you just continue to pass that around, and anyone who hasn't signed in can sign in. Okay. So let's see. Starting off, let's see with chapter 5. Okay, we've got basically you got to know 3 different types of acids and bases. Okay, we've got the Arrhenius theory, Bronsted-Lowry, and the Lewis acids and bases. Okay, we'll talk about that. Maybe probably go through a little bit with the strong acids and bases, weak, and polyprotic. Okay, just kind of hit each thing in line here.
Where can you get that?
That should be on your. What was it?
Sapling. Is it? Oh, thank you. Okay.
Yeah. And one of your classmates gave me these, so you guys should have access to them. Okay, so I'm going to go ahead and I'm going to start with the different types of acids and bases. All right, and we can just kind of go from there. All right, so we've got 3 types of acids and bases. Like we said, we've got the. Seriously. That's what I'm thinking. This is where I need to be. I'm used to whiteboards. Alright, so.
You have to press the little down there where it says pens. Right, see where it's blue?
Here?
There you go. No.
There we go. Okay, so we've got 3 types of acids and bases. We've got Arrhenius, Brunson Lowry. Right, and then we've got Lewis. Okay. And the thing about these is, as you go down, your definition gets less specific. Okay. So basically, what that allows us to do is encompass more compounds as acids and bases. Okay. I'll show you guys examples so that you see what we mean here. Okay. So let's see. Acid, base. Okay. So with our three definitions here, we start with arrhenius. Anyone tell me what is an arrhenius acid? Anyone knows?
The acids have hydrogen attached to them, H+.
On the right track, right? Yeah, so we gonna have H plus. That's one half the definition. The other half is really important. That's gonna be Brunson Lowry. The other specific part of this is it's gonna form H plus in water. Okay. So if that's the acid definition, what do you guys think the base definition is gonna be? I heard someone say it. Okay, it forms hydroxide ions in water. Okay. So, okay, those are both two pretty specific definitions. We have to be forming H plus in water, and we have to be forming hydroxide in water. Okay. Brunson-Lowry gives us a more general definition here. And what was the definition you gave just before?
Proton.
Okay, which one is that, the acid or the base? Okay. So we have proton donor. Okay, and what is a proton? That's just H plus. Okay, and then a base has to be what? Has to be a proton acceptor. Okay. Proton donor, proton acceptor. Now, Lewis. Some people came in earlier to the ARC, they weren't really sure what Lewis acids and bases were. But where have you guys seen Lewis before? Lewis structures. What's the big thing with Lewis structures? The electrons. Okay, so Lewis, we're talking about electron pairs. Okay, those are what's being donated or accepted. Okay, so in this case, which one is the electron pair acceptor? Okay, the acid. Okay, electron pair acceptor, and so then that makes our base the electron pair donor. Yeah. All right, so like we said, it gets less specific the further we go down. Okay, so anything that's a Lewis acid, okay, let's make sure I got this right. No. Anything that's an arrhenius acid would be considered a Brunson-Lowry acid, would be considered a Lewis acid. Okay, we start out with something like, what's a good general acid, you guys know? HCl. Okay, hydrochloric acid. Okay, so what would be the Arrhenius? Like, what kind of equation would you give me to show the Arrhenius definition using HCl? Okay, we got the in water, so plus H2O. Okay. One more.
The two arrows.
Okay, so she's saying Okay, so we're going to be forming H3O plus Cl minus. All right, you guys agree with all that?
Since HCl is a strong acid, do you not need the equilibrium arrows?
Exactly. Okay, this would be incorrect. Okay, you don't want to put the double arrow on here because, like you said, HCl is one of the strong acids. So remember, complete dissociation. Okay, just a single arrow. Okay. All right. Yeah, a lot of the Bronsted-Lowry stuff, you use the same type of equation. We're mostly talking about doing this in an aqueous solution. Okay, so there's still going to be water in there. Okay. In this case, if we're talking about the Bronsted-Lowry definition, what is my proton donor here? Okay, HCl. Okay, so that's put PD, proton donor. Okay, and so then that makes water, that's going to be my proton acceptor, right? Because it's forming H3O plus. Okay. Now, like Lewis acid to bases, things get a little more hectic here because it doesn't have to be in water, right? And it doesn't have to have a proton. Okay, so can anyone give me an example of something that's a Lewis acid or base? Okay.
I know it's BF3, and then I think it's no, maybe I don't know.
You're right. So BF3. Okay. Now, can anyone tell me, is that an acid or a base, though?
Base.
I'm hearing both here. Okay, so one person thinks it's an acid, and I think the rest of people sounds like think it's a base. All right. Well, let's see here. If I were to, say, put this in with ammonia, is a reaction going to happen? Inquisitive looks. All right. A reaction does happen. Okay, in this case, we're going to be forming BF3, and it's going to be bonding to the nitrogen. Okay, so is BF3 an acid or a base? It's an acid.
Okay.
Okay, because if we look at this here, what we have going on is nitrogen has that lone pair of electrons on ammonia, right? Okay, and what's special about boron? It was one of your exceptions to the octet rule. You guys are mumbling. I speak up. I'm old. I can't hear. Well, what's special about the way boron can hold electrons?
To complete like the octet would be with just 6 electrons.
Right. Boron can be happy with only 6 electrons. Okay. If you were to draw out the structure here, you have boron, fluorine, 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 right? The fluorines all have octets. The boron only has those 6 electrons from the bonds, okay? And boron's okay with that, okay? But what can happen is those electrons, they can come over and they can attack that boron and form a bond, okay? So even though there's no exchange of protons, okay, this is still considered an acid-base reaction under the Lewis definition. Okay, But because there's no protons being exchanged, okay, it's not going to be a Brunstad-Lowry, it's not going to be an Arrhenius. Okay? Up here, is there going to be that electron exchange in the HCl in the water? What do you guys think? Yeah, it's still going to be there. Okay, where are the electrons that are doing the donating? What atom are they on?
Chlorine.
Chlorine's a good guess. It's got 3 lone pairs, right? What else has lone pairs? Oxygen. Right? So what's happening here is those lone pairs on oxygen, they're picking up that proton. Okay? Remember, in water, HCl is going to break up completely. Okay? So you're going to get H+. H+ has no electrons whatsoever. Okay? So it's going to be something really, that can handle more electrons really well because it has them. Okay? So that lone pair is going to come over, pick up that H+, okay, and it's going to give you your H3O+. Okay? So this works under the Arrhenius, Brunstad-Lowry, and the Lewis definitions. Okay? But this one doesn't because we don't have that proton exchange happening. Okay? Make sense? See some kind of confused faces.
For this part, we also need to know the conjugate base, conjugate acid.
We can talk about conjugate acids and bases. All right. What is a conjugate acid and conjugate base?
They're like the pairs, like the HCl and the Cl minus.
Okay, HCl and Cl minus. Okay. So that's one pair. And then we've got the H2O and H3O plus. All right. And other examples would be, let's see, like H2SO4. So that's an acid. What's going to be the conjugate base of H2SO4? HSO4 minus. Okay. What about sulfate? SO4 2 minus. Well, if it's an acid, right, it doesn't really have any lone pairs it's going to donate. It doesn't have a proton to donate, right? Okay, this is a base. Okay, so it's going to, it does have lone pairs to donate. It doesn't have a proton to donate. Okay, so it's going to be a base, right? It can take on another H+. In which case, what do I get? I get these two, H2SO4 and HSO4, and then HSO4 1 minus and SO4 2 minus. They're also conjugate acid base pair. Okay. What about H2SO4 and SO4 2 minus? Are they related by conjugate acid base pairs? No, because you have to have only one proton different. Okay? If I were to go from H2SO4 to SO4 2 minus, I have to lose 2 protons, right? Okay, so they're not a conjugate acid base pair. Okay, it can only differ by 1 proton. Okay? This brings me to something else. Anyone notice anything special about the HSO4 minus? I mean, it's both.
An acid and a base.
It's both an acid and a base, okay, depending on what it's going to be reacting with. Okay, so what do you call a molecule that can act as both an acid or a base? Amphoteric. so amphoteric can be an acid or base, depending on what you're reacting it with. Okay? How are we doing so far? Okay, questions? Okay, I'm going to erase this stuff over here. Okay. What do we have next on there? Oh, wrong thing. Okay, so we talked about the three definitions. Okay. Let's see. How you guys with your self-ionization of water? Like, what is the self-ionization? What does that mean?
When the H2O goes to the H3O plus.
Okay. Right, so you have two water molecules. One's going to act like an acid. The other one's going to act like a base. Right? And so when they react, you're going to form H3O plus and OH minus. Right? And so in pure neutral water, you're going to have the same amount of H3O plus as you do OH minus. Right? Okay. And can anyone tell me, at 25 degrees Celsius with pure water, what are those concentrations? H3O plus and OH minus.
1.0 times 10 to the negative 7.
All right, each one's going to be 1 times 10 to the negative 7 molar. Okay? All right, we're going to get to that here in a little bit. Let's see. Yeah, I'm not going to go through it all, but you guys can access this online. Okay, make sure you guys know your strong acids and your strong bases. Okay, because as long as you know those, if you come across anything else, you know it's weak. Okay, and what's the main difference between a strong acid or base and a weak acid or base? Marcos?
Well, wouldn't for one of them, like if you had a solid, you would have to use the ice table, well, for the other one it associates to water and.
That is true, but if we want the actual definition of a strong acid, it completely dissociates. All right, remember HCl is completely breaking up into H plus and Cl minus. Okay, but something like HF, that's a weak acid, that's going to be going back and forth. Most of it will stay as HF. Okay. But yeah, if you can just remember, those 6 strong acids, and there's only a few strong bases. Okay, if you just remember those ones, anything else you come across, okay, it's going to be weak. What would you expect for a Ka value for a strong acid?
Something really large.
Something very big. Okay, larger than 1. Okay, most of your other weak ones will be less than 1, right? Like 10 to the minus 4, 5, 8, 12. Okay. Let's look at some calculating pH. Okay. You guys said before, if I was to calculate the pH, let's say if it was, let's just go with like 1.5 molar HCl. Okay. Strong acid, right? So how are we going to calculate pH here? What is the formula for pH? Negative log. What?
H plus.
Okay, of our H plus concentration, right? Okay, so in this case, what is my H plus concentration? What's that going to be?
1.5 molar.
Okay, it's going to be 1.5. Right, and remember, we know that because complete dissociation. Okay, so all that breaks up, that's going to be all that we have. So negative log of 1.5. Anyone have a calculator on? An answer?
Negative 0.17.
Negative 0.17. Okay, so let's double check ourselves. Does that make sense? No, I hear someone say no. Does?
pOH can be more than 14.
Okay, POH can be more than 14. pH can be less than 0. Okay, and the pH scale is not hard and fast, to start at 0 and stop at 14. You can go below 0, you can go above 14. Okay? One thing that I always remember is that anytime you have a strong acid that's 1 molar, what's the pH of a 1 molar strong acid solution? What's the negative log of 1? 0. Okay, so if you have something that's greater concentration than 1, if it's completely dissociating, then you're going to end up with negative pH values. Okay, so a negative 0.17, that's not out of the realm of possibility. Okay. All right. I had an example here, kind of tying into one of the other chapters with the titrations. How are you guys with your titrations? Kind of. Can anyone tell me what a titration is? Okay, you're neutralizing. Well, what's the point of a titration?
Find the pH of the acid.
Say again.
Find the pH of an acid.
Okay. Yeah, where we're getting there. So the whole point of a titration is you're taking, with acids and bases, a lot of time you're taking something that you don't know what its concentration is. Okay, and you're taking, say, like an acid. You're going to take a base that you do know its concentration. Okay, and you're going to add that base in very small amounts until you neutralize that acid. Okay, you guys done this one in the lab yet? Mm-hmm. Okay, so you guys at least have done titrations. Okay, so let's take a look at an example. This one's asking to find the pH, okay, of 100 milliliters of a 0.2 molar acetic acid solution. Okay, so acetic acid, CH3COOH. Okay, the Ka value is 1.8 times 10 to the negative 5th. Okay, so that's our, so yeah, this is going to be the analog. This is the one we're adding the base to. Okay. All right, and we're going to be adding 0.1 molar potassium hydroxide. okay? And we're going to be looking at some different volumes of potassium hydroxide, and we're going to see how do we calculate the pH at those volumes, okay? So before we do that, real quick, acetic acid, is that a strong or a weak acid?
Weak.
How do we know?
Because it's very strong.
Right. It's not one of those 6 strong acids. Anytime you see COOH, or it might be like COO, the H might be over here, or it could be CO2H, okay? If you ever see anything like that, it's an organic acid, okay? Those are all weak acids, okay? So we got a weak acid. What about potassium hydroxide? Strong or weak? Strong. Okay, that's one of our hydroxide, group 1 metal hydroxides. Okay, so really, the potassium, that K, are we concerned about that K at all? Is that going to affect our pH? No. The strong, the conjugate acid of a strong base is not going to affect pH. Okay, so really what we're concerned about here is this is 0.1 molar OH minus. Okay, that's what we care about. Right, so real quick, if we were to say add in 0 milliliters of that potassium hydroxide, how are we going to calculate pH? We're just trying to calculate the pH of a weak acid here, right? So what do you have to do to calculate the pH of a weak acid?
Use the chart.
Okay, we got to use the chart. Okay. Okay, so first off, our reaction. What's the reaction that's happening here? If it's a weak acid, is it going to be donating a proton or gaining a proton? It's going to be donating a proton. So we're going to start off CH3, COOH, double or single arrow? Double arrow. Okay. And so I'm going to be giving up H plus, and then whatever's left over, right? CH3COO minus. Okay? I'm plugging in my molarities here, so what's my molarity of the acetic acid? Okay, starting off with 0.2. Excuse me, what about H plus? None of it's been formed yet initially, and none of the acetate has been formed either. Okay, so both those are going to be 0. What about my change? Okay, that's what we're looking for, right? So, you know, it's going to be minus X. Over here, we're forming it, so plus X, plus X. Those ones are going to be X, X, and 0.2 minus X. Okay, so those are my equilibrium concentrations. How am I going to find out what the H plus concentration is, right? That's how I'm going to find pH. So I need to find my H plus.
Use the Ka formula.
Okay, so I got Ka. That's 1.8 times 10 to the negative 5th. Right, and so how am I going to get all this stuff in there? How does it plug in?
Wouldn't it be x squared over 0.2 minus x?
Right, remember products over reactants. So x times x, or we're just going to do x squared over our reactants concentration 0.2 minus x. Okay. I emailed Dr. Hawk, and he said one of the things that people were getting confused about was this minus x part, right? because one of the assumptions you can make is you can ignore that x, right? And so we need to know when can we ignore that x. Okay, so right now, if we were to just ignore it, okay, now we're going to have 1.8 times 10 to the minus fifth is equal to x squared over 0.2. Okay, so if that's our equation, assuming that minus x doesn't matter, okay, what does x come out to be? What is it? 0.002. Okay, so now we need to double check, make sure that the assumption we made is valid, right? So basically, if this concentration here, this x value, if that is equal to or less than 5% of the original concentration you started with, that's a valid assumption. Okay, so if we had 0.002 over 0.2 times 100, what is that? Was it? Okay, so is our assumption valid here? Yeah, okay, because what we're saying here is this Ka value is very small. Okay, so equilibrium is lying more over here on this side. Okay, only 1% of that acetic acid is dissociating. Okay, so we can make the assumption that the concentration doesn't really change that much. Okay, 0.002 is not going to take away very much from 0.2. Okay, it'll be basically the same number. Okay, I don't know about how his rules are with calculators, but I know with my calculator I can just plug in this entire formula and it can solve and give me my x. Okay. If you guys got a calculator like that, you can just plug in everything, including that minus x term, you're golden. Okay. The biggest problem I think a lot of people have is that they go and they assume to get rid of that x, and then they forget to double check it. Okay, because if it's something like 6%, 10%, okay, then that assumption's not valid. You have to go plug it back in and solve for x using the quadratic formula. Okay. So, just I'll say that if you guys have something like a program on your calculator that you can solve it, okay, then you don't have to worry about, do I leave it out or do I not? Okay, you just always have it in there. Okay. All right. So now this x, this is my H plus concentration, right? All right. So then, what's my pH? Right, negative log of 0.002, which is right. Okay, 2.7, roughly. I think, yeah, 2.72. Okay, so before you add any base, okay, we're at 2.7. Okay, so this one's relatively easy. Okay, we haven't even added any of the base yet. Once we go and start adding base, then that's when things get a little bit more difficult. A little bit more steps are involved. Okay, so should we look at one of those?
Yes.
All right. So, can I get rid of this stuff over here? Okay, so let's go ahead, let's skip ahead, let's go to adding 100 milliliters of the potassium hydroxide. So after you started adding the base, now you've got to break the problem down into two different steps. Okay? The first step is going to be your neutralization. Okay, you've got acid, you've got base in there. Okay, they're going to react until one of them gets used up, or both of them get used up. Okay, so you got to figure out, first of all, which one gets used up, how much of the other one's left over, and then you can go ahead and calculate the pH from there. Okay, so with a neutralization reaction, what's going to happen there? What happens in a neutralization reaction? It's going to be my reaction happening. Okay, we're trying to get to pH 7. Okay. I want to know what's the chemical equation. We know we've got acetic acid in there. And so what's it going to be reacting with? KOH. Okay, we said the only part we're really concerned about is the hydroxide. Okay, this is neutralization, so it's going to be a single arrow. Okay, anytime we have neutralization, what's going to be forming? We're going to be forming H2O. And what's going to be left over? All right, the acetate ion. Okay? So we're going to kind of set this up the same way. Okay? Except I would make sure, okay, you guys, we're going to be using moles here. Okay? The other ice tables we're using molarities. Okay? But here we want to convert those into moles. Okay? And remember, what's the formula for molarity? Right. Moles over liters. Okay? So we have molarities, we have volumes. Okay? We should be able to calculate the moles of each one of those. Question?
I just have a question. Why would you use moles here instead of molarity? Like when is the time that you know you use moles?
So think about, remember doing limiting reactant problems? Okay, this is a limiting reactant problem. Okay, remember when you did those, you had to get them both into moles first. And then you could see, okay, they're in a 1-to-1 ratio. Okay, so if I had, say, 2 moles here and 1 mole here, I know that 1 mole is going to get used up first. I'm going to have 1 mole left, 0 moles, and then whatever gets made. Right? So it's the same idea. We can't compare molarities directly, but we can compare moles directly. Okay? Right? So if we were to solve for moles here, just multiplying our concentrations by our volumes. Remember, volumes, milliliters should be converted into liters. Okay, I'll just tell you guys we're here at 0.02, 0.01. Water doesn't matter. Why doesn't water matter? Because it's a pure liquid. Okay, and there's no acetate yet. Okay, we're assuming no dissociation yet. Okay, so obviously, which one's going to be used up first? Which one's last? The OH. Okay, so we're going to be forming 0.01. That's gone. Okay, and this one's down to 0.01. Okay. So now I can go ahead, I can convert these back into molarities, and I could use another ice table to find out how much of this is dissociating, how much H plus is being formed, right? So, first of all, what's my total volume? That's important here. Okay, we started off with 200, we added, 100, we Add another 100. So we're at 200 milliliters now. Okay, so if I were to divide that by 0.2 liters, and that by 0.2 liters, what is, I don't have that, what's 0.01 divided by 2?
0.05.
0.05? Yeah, that makes sense, doesn't it?
0.01 divided by 2, or 0.2, okay. I was gonna say.
Okay. So we have those concentrations. We could, go the long way, set up another ice table. Is it okay if I just abbreviate HA? We all understand that. That's HA. Okay. So that will be breaking up like we had before into H plus and A minus. So we can plug in those. Let's see, no H plus is formed yet. But what about A minus?
The 0.01.
It's going to, I'm sorry, I put 0.2.
Oh, the 0.05.
0.05, 0.05. Okay, and you can go through and do this the same way. Minus x, plus x, plus x. Okay, you can do it like we did the last time. Set this all equal to Ka and solve for it. Okay, does anyone know an easier method than going through all that again? Anyone remember the Henderson-Hasselbalch equation? A couple people. What was the Henderson-Hasselbalch?
PK plus the log of acid over, no, the base over acid.
Is equal to what?
The log of base over acid. So A minus.
All right, well, that's half of it. What's the other side? What's all that equal to?
pH.
That's pH. Okay, so you can use this equation as a time saver. Okay, because it will basically get rid of all this down here. We have Ka, so how do we find pKa? Just take the negative log of the Ka. Okay, if we do that, of course I don't have that written down either. Real quick, what's that's like 4.74? That what that is?
Yeah, or 4.7.
Okay, so the pKa is 4.74. Okay, what we can do now is we can plug in pKa, we can plug in our two concentrations. Okay, really, you could just plug in the moles because they're a ratio. So the volumes would just cancel each other out anyway. Okay, but if we were to do that, let's see, I'll use a different color over here. We've got pH is equal to 4.74 plus log of, say, 0.05 over 0.05. Okay, so our ratio is 1. What's the log of 1? 0. Okay, so in this case, pH is equal to pKa, 4.74. Right. This is an important part. Did you guys in lab, did you do the experiment where you had to calculate the Ka of a weak acid? No? Okay, well, this is how you would do it. You would titrate this is what we call the halfway point, right? Because we've used up half of the acid. Okay, and so then at that point, pH is equal to pKa. Okay, and you can find the Ka value from there. Okay? Question?
Can you just rewrite the volume and the concentrations again of each solution?
I'm sorry, say that again?
The volume and the corresponding concentration. Can you just rewrite it? Because I don't know what concentration goes with.
Oh, sorry. So,
It's okay.
let's
I
see.
mean, like, just like the problem that we're doing, like the question, like.
Okay, so we start off with 100 mils of the 0.2 molar. Okay, and we're adding 100 milliliters of the 0.1 molar hydroxide.
It was the same as last one or something.
All right, how are we doing here?
Can we use that pH equals pKa for like the last example as well, or do we have to use the?
So let's see, the last one we did, that was the 0 mils, right?
Yeah.
Well, why don't you guys tell me, can we use the Henderson-Hasselbalch when we had the 0 mils? Did that happen? Right, because at that point, you don't know how much of the conjugate base there is. Okay, so here, because we're starting with some of the conjugate base, that's why we can use it. Okay, you'd have to go through, do the ice table for the other one. Okay. Let's see here. Yeah, in theory, we could go through, we could do how many mils of the hydroxide is going to be required to reach the equivalence point. Anyone tell me? What happens at the equivalence point? Anyone tell me the definition of the equivalence point? Anything about it?
Isn't the H plus concentration equal to the OH minus concentration?
Right. Okay, the equivalence point, that's where H plus concentration equals OH minus concentration. Okay, so we'd have to add in just enough of the base to completely neutralize the acid without going over. Get this stuff out of the way. Okay, I just want to quickly go through one last one. Okay, 200 milliliters potassium hydroxide. This is going to be the equivalence point. Okay. So, if we're putting this stuff in here, okay, just like we did before, you could plug in, let's say we had HA plus OH minus gives us water A minus. Okay, and so we had 0.02. Okay, remember this is moles. Okay, 200 times 0.1. Oh, I'm sorry, 200 milliliters, so 0.2 times 0.1 is how many moles? 0.02. Okay, so we have the same moles of acid and base. Water doesn't matter. We don't have any of that. Okay, so both of those are going to get used up. None of that left. And this is going to be 0.02. All the acid gets converted to the conjugate base.
Wait, can you just repeat again where the 0.02 for the OH minus came from?
Because we had 200 milliliters, so 0.2
Oh.
liters times concentration. Okay? So we still want to find pH. Okay, but there's no more acid left. So how do we go about doing that? What are we gonna have to do here? Use Kb, right? Because all that's left in our solution now is the conjugate base. Okay? So, let's see, what's going to be my total volume here? Okay, we're up at the 300 milliliters now. Okay, so at 300 milliliters, what's my concentration of conjugate base? What is it? O2? Oh, that's the moles. So moles divided by 0.3 should be 0.067 molar. Okay. All right. Let's see. You said we have to use kb.
Yeah.
I don't have a kb. What am I going to do? Sorry.
Use Ka to find it.
Use Ka. Okay. And how do we relate Ka, Kb? Kw. Okay. So if I want to find Kb, that's equal to Kw over Ka. What's my value of Kw at 25 degrees Celsius? 1 times 10 to the minus 14. That's going to be over 1.8 times 10 to the minus 5. Therefore, our Kb is 5.56 times 10 to the negative 10. Okay. So if I were to come over here real quick and do a small one over here, what's the reactions going to be happening? I have in here, the only thing I have left, remember, is the A minus. So what's that going to be reacting with? Reacting with water. Single arrow or double arrow? It's going to be a double arrow, right? And we don't have any strong acids or bases in here. And what am I going to be forming? Well, is this an acid or a base? It's going to be a base, right? So that's going to take a proton. We're going to reform the acid. And what's left over from water? OH minus. Okay? So we can plug in what we know. Okay, water doesn't matter. Those are 0. Okay, so down here, we're going to end up with 0.67 minus x. And here we're going to have x and x. All right, so I'm going to plug back into my Kb, right? I'm going to solve for x. So remember, products over reactants, so x squared over 0.067 minus x. Are we going to be able to ignore that minus x? Should be able to. I don't remember right. Of course, I don't have it right now. All right. Well, we can always find out, right? If we ignore that, okay, solve for x, what do we get? Say it again?
3.7 times 10 to the negative 11. I mean, 6.1 times 10 to the negative 6.
1 times 10 to the negative 6. Okay, is that less than 5% of the original concentration we started with? No, that's way less, right? You know, think about it, it's not very much is dissociating at all. Okay, so that's way less. So this X, what is that? What's that represent? That's the OH minus concentration. Right, we're not done yet. Okay, so from OH minus, I can find POH, right? So my POH, I'll put over here, ends up to be 5.22. Therefore, my pH is 8.78. So remember, how are pH and POH related? -14. Right. 14 equals pH plus POH. Okay. So this is the equivalence point, right? All my acid's been neutralized. So why is my pH greater than 7? Because it was a weak acid. Okay, and because it's a weak acid, what's that telling me about its conjugate base? Right, it's strong, so it's going to deprotonate water. Okay, and so by deprotonating water, that's why we had this reaction here. Okay, it forms OH minus. That OH minus pushes pH up. Right? Okay, and that's why we're getting 8.78 as our pH. Okay? I still see some people that are kind of confused here. Questions? Let's stop here for a second and think of questions.
How did you know that you had to use KB?
Because it was A minus.
Right, because we used up all the HA, and so all we were left with was the conjugate base. Okay, anytime we use a base, we want to use KBs. Okay. Yeah.
Since our concentration of OH was like 10 to the negative 6, would we have to put in the concentration of OH due to like the water?
It's a good question.
Would water change it just like slightly?
Let's see. Well, if we were to say, KW, right? 1 times 10 to the minus 14. Okay, that's if we were to go ahead and say, let's plug that in for, we're going to solve for H plus. And if we plug in this concentration of OH, 1 times 10 minus 6, what do we get for H plus concentration? Sorry, kind of ran together there. Trying to solve for the H plus concentration here.
Okay. H plus 1, we just take 10 to the negative 8.7.
Oh, because he was asking if we have to take into account the ionization of water.
Oh.
Okay, and I'm trying to make sure I'm not confusing myself here. Let's see, did Dr. Hawk, did he give you guys like a cutoff or when to accept the auto ionization? Anything like that? Well, at this point, I said, honestly, I don't know. I don't know what the cutoff would be.
I'm just gonna assume that on a test, he's not gonna expect that.
I will not confirm nor deny or say anything about that. Okay? So how are we doing with the titration stuff?
So like we did the last example where we found the pKa, could we do that with this too, where we found the pKb and then found the pH, or does that not?
Say that again.
So like in the last example where we did the 100 milliliters, and we found the pKa to find the pH, could we do that with this too?
Well,
With pKa?
the pKa, that only worked because it was at the halfway point. Okay, and with, we were really using the Henderson-Hasselbalch. And it just happened that the other part went to 0. Okay, so you can't use that because just like when we were trying to find the concentration of the acid before any base, remember we only had the acid to start with. We didn't have any of the conjugate base to put in there. Okay, it's the same idea here. We're only starting with the conjugate base. We don't know how much of the acid's going to be produced. Okay, but if you have both of them, then by all means you can use that.
I think to answer the question, it's because we already know that there already is an excess of OH, so then that would make the solution basic. And we solve for pH that's already basic, so you wouldn't have to take into consideration of the water. I feel like only time where you would take that into account is if you know that it is basic, but the pH is acidic, so slightly less than 7. So then that's when you would take it into account.
I see what you're saying. And I don't want to say anything more. I don't want to mislead you. Okay. I'll just say I'm not entirely sure. Okay. All right.
What's the blue reaction? The one right in
This one over here.
So the green one is neutralization, and the blue one is
All right. So remember, up here we got rid of all the acid and all the base. Okay. So down here. If you go back to the first one we did, we had the reaction where it was HA breaks up into A minus and H plus. Okay, this is basically the same kind of thing. We only have A minus. Okay, so it's going to react with the water to give us back HA and OH minus. Okay. All right, I feel like we're kind of like being a dead horse with these calculations. Okay, should we talk about something else? How are you guys with identifying pH curves, titration curves? Like, can anyone tell me what a titration curve looks like? Can anyone come up here and draw one for me? Go away. Would anyone feel like coming up here and drawing a pH curve?
I did on Monday. She's done, she would sit around. No, we probably do it in the spring together. I don't know, idea.
All right. You think you can come up with a problem, or you have a question?
I had a really quick question.
Yeah.
So at the half equivalent point, pH is equal to pKa, right?
Correct.
For monoprotic acids. What about polyprotic acids? Because they have multiple pKas.
Then I'm not entirely sure. I think you'd have to, like when you're going through, let's say if we were looking at the pH curve for a polyprotic acid, then you're gonna have something like that. Okay. So you're going to have the equivalence point for the first one there. The second one's going to be there. Okay. So the first half equivalence point is going to be right there.
Yeah.
All right. And so what I would assume then is that the second half equivalence point would be, it's going to be, let's say this is x. So then this would be half x.
So it's going to be.
Basically, I think once you reach the first equivalence point, you got to start over again. And it's going to be halfway from that point to the next equivalence point.
Oh, so then at like the second half equivalence point, pH will be equal to pK2?
Right. I think that's the way it should work out.
Okay.
That's the way it makes sense. Okay.
Thank you.
Okay. So we've kind of drawn a 1 pH curve here. Okay, this is for a polyprotic, a diprotic acid. What's going to be on my y-axis? pH. Okay. Plotting pH over here, and what's on my x-axis? Okay. Well, specifically milliliters. Like what? That's the unit, but what is it we're actually plotting? Volume of the titrate. All right, and which one's the titrate? Is that the one your acid, your unknown, or is that the one that's up in the burette? That's the one up in the burette. That's when you add to your unknown. Okay? So I got no takers. No one thinks they could draw the curve for a weak acid being titrated with a strong base. Here we go, 7.
What's the one there?
That would be for a diprotic acid. Okay. Well, if we're starting with a weak acid, where's my pH going to be?
Like it's gonna be like between 0 and 7, probably like low, like 2 or 4.
Yeah, we're gonna start down here. Okay, and so your pH curve, your titration curves, they all follow the same sort of shape, right? It's kind of that squared off S shape, right? So it's gonna be kind of flat, jumps up, and then it flattens off again. Okay. So on here, where is my equivalence point going to be? How do we find the equivalence point? Any guesses? Okay, so the equivalence point, you see this vertical region here. Okay, essentially what's happened is, here we're adding base, the base is getting used up, okay, and so we're maintaining roughly the same pH, okay, but then as we're getting closer and closer to using up all the H+, it starts increasing again, and all of a sudden there's going to be this big jump when now we've used up all the H+, and now we have excess OH-. Okay, and that's going to push pH way up here. So about halfway between, that's going to be your equivalence point. Okay, and if I've drawn this correctly, do you guys agree with that, where my equivalence point lies as far as the pH is concerned? Think about the example we just did. That last one that we did was the equivalence point, right? pH was like 8 point something. Okay. Why did the pH get pushed up?
Because of the strong base.
Because it was the conjugate base. The conjugate base, remember, it was producing OH-. Okay, and so at the equivalence point, Okay, we're not going to be at exactly 7. Okay. Could anyone tell me when would you expect the equivalence point to be exactly at 7? There's 2 times you could expect that.
Would one of them would be when you make the strong base with a strong acid?
Strong base, strong acid. Okay, because their conjugate base, conjugate acid aren't going to play with water. They're not going to do anything there. Okay? But what would be the other time? Special time when you have weak acid, weak base. It's going to be when your Ka and the Kb values are the same. Right, so I think, if I remember right off the top of my head, if you look at the Ka value, I think it's acetic acid, one we just used, and I think ammonia. The Ka and Kb values are the same. Okay, and so their corresponding conjugate acid, conjugate base, Ka, Kb values, they're also going to be the same. Okay, and so they neither one dominates the equilibrium. Okay, and so that's going to make it at pH equals 7. Okay, so either strong acid, strong base, or weak acid, weak base with Ka equal to Kb. Okay. Right. What else was there with the acid stuff? Okay. Can I give this stuff a quick glance through, see if you guys have any questions about any of the stuff that's on there specifically. Otherwise, we can move on. All right. Would you guys rather do buffers or the KSP stuff? Buffers? Okay. And what time we at? 7. Okay. All right, so buffers, the thing I'll tell you guys is as soon as you see something with buffers, just immediately go to Henderson-Hasselbalch. That's going to solve like 95% of your buffer problems. Okay, as long as you got the concepts down. All right. Why don't we go, let's talk a little bit about like what makes a good buffer. What makes a good buffer? In order to be a buffer, what do you have to have?
So weak acid and a weak base together,
Right, so you have either a weak acid or a weak base, and its conjugate base/acid. Okay, it's important that you have the conjugate. Okay. Okay, so you have that weak acid, weak base, corresponding conjugate. What else? You have to have, let's see, you want to choose one that has a pKa or pKb value close to the desired pH or pOH. All right. So, for example, if you wanted to keep it buffered at pH 6, okay, you're going to choose one that has a pKa of like 5.8. All right. right, or 6.4. You're not going to choose one with a pKa value of 2, okay? Because you can still make a buffer solution at 6, but it's not going to last for very long, okay? Because if we think about it, first of all, before we even talk about what makes a good buffer, what is a buffer? What's the whole point of a buffer solution?
It resists changes in pH when a strong acid or a strong base is added to it.
Right, so you add small amounts of H plus or OH minus, and that pH of that solution should not change. Okay? That's what's going to be a buffer. Okay, so to do that, we need the weak acid, weak base, pKa close to your desired pH. Let's see, we also need the ratio of the conjugate base over the acid. Where have we seen that before? Where have we seen that ratio before? It's the Harrison-Hasselbalch, right? Okay, we want that as close to 1 as we can get. Okay, and remember when it's equal to 1, what happens to pH? It equals what? Doesn't equal 0. pH, what does pH equal? The pKa. Right? Okay, there's an Hasselbalch up there. Okay, so we want to try and get that to 1. Okay, and then the last one. Okay, we want high buffer capacity. Okay, basically what that means is we want high concentrations of A minus and HA. Okay, the bigger those concentrations are, the more H plus and OH minus they can absorb. Okay, so we'll just say high concentrations. Okay, so that's what's going to make a good buffer. I got 2 examples we could go through. One's asking, it's giving you the buffer, it's asking you how much base of the conjugate base you would add. And then the other one's giving you a list of different ones you can choose from. Pick which one would be the right buffer. All right, so which one would you guys prefer to go through first? The first one? That sound all right? Okay. Can I get rid of this stuff? Yeah. There we go. That's fine.
I'm pretty sure you could just keep scrolling down too if you want.
Does it?
Yeah.
No.
Yeah.
It's fine. Okay, so I wish I had a way to project this on there. Okay, if I had 400 mils of 1 molar formic acid, okay, it wants to know how much sodium formate to buffer at a pH of 3.5. Okay, and I'll give you guys, the Ka for formic acid is 1.8 times 10 to the negative 4. So where do you guys think we're going to start here? If I see buffer, where should I go to first? What should I think about?
Henderson-Hasselbalch equation.
Henderson-Hasselbalch equation. Okay, so I've already got pH, right? I can find pKa. So I'm really looking for my ratio, right? Specifically, actually, I know my concentration of HA, right? That's given to me up here. So really, I'm just looking for the concentration of the A minus. Okay, so this one's pretty simple. All we gotta do is plug and chug, right? Okay, so if I'm gonna set this up, I know 3.5 is equal to, let's see, negative, sorry, what was it? 3.73?
3.74.
74, okay. Plus the log A minus over 1. Okay? So if I do a little bit of rearranging here, the log of A minus then is equal to negative 0.24. How am I going to get rid of the log? I take 10 to the power of both sides, right? Okay, so therefore, A minus concentration, 10 to both sides, I end up with 0.575 molar. So that's my concentration of the sodium formate, the NaHCOO.
Can you please explain one more time how you found out the pKa?
pKa, that's just take the negative log of pKa.
It's the same as pH. Except the concentration plus. It's just
Thank you.
Okay. Anytime you see P, just negative log of whatever that is. Okay.
Thank you.
Right?
So,
So how is that?
is that the answer?
Well, we can go ahead and we could take that, we don't necessarily use molarities, right? If I wanted to know how much of something to add, right, if this is like a solid salt, how are you going to measure that out? Grams. So and if I'm starting off then, if I take my 0.575, say, moles per liter, how am I going to get that in grams? Okay, molar mass. So if we do that, molar mass of that is 68. That's grams per mole. Right, and that's all going into 400 milliliters. So we have to multiply that by 0.4 liters. So if we plug and chug all that, we end up with 15.64 grams. That's how much you'd have to add to make that into a buffer solution of 3.5. Okay. On the exam, I'd always check to make sure, what it is exactly you're looking for. And are you going to stop down here at the concentration, or does he want it in grams? What exactly does he want the answer in? Okay.
I'm serious.
Okay, so how's this? Okay, nothing too hectic. All right. All right, should we do another buffer example? Okay.
With like polyprotic acid?
Sorry?
Do you have any examples of like polyprotic acid?
I can find one real quick. It wouldn't be a buffer problem, but would you guys want to look at a polyprotic one?
Yeah, he just emailed us like the main things for the exam.
Oh, did he?
You wanna look at it?
Let's take a look real quick.
What is
Oh,
the
yeah.
fair game? That's what I said.
Uh-huh.
Important.
All right, let's see. See, what are the different types of acids? Okay, what is pKa, Ka, pKb, pOH? What are the properties of acids and bases? Identity, mechanism, strengths. Okay, so I guess he's talking about, identify acids and bases, like which one's taking a proton, which one gives up the proton, that sort of thing. What is a buffer and how do they work? Okay, so that's just what we did just before. Right, conceptual and mathematical treatments. Fair enough. Polyprotic acids, I can find one real quick. We did some titration, KSP and solubility, determining solubility, common ion, complex ions. And he says, good luck. All right, so I can pull up a polyprotic acid example.
No, I think he taught him like in general, but I didn't. Nothing like it was canceled or something. Cute, is about. That's true.
Also, somebody said she was there at the end.
Yeah, she was handing back quizzes that we went.
Okay, good. Yeah, I was nervous.
You what?
Okay, so here's a
You just told
here's a polyprotic one. Look at that.
Oh, there's a button at the bottom.
Extend page.
Is it obvious that
I had a couple teachers that had these in high school.
Okay, so we're talking Okay, we have a solution, 0.7 molar citric acid. Okay, this is polyprotein. Right, and so the formula for that is H3C6 H5O7. Okay, I'm not going to draw the whole structure for you guys. Yeah. It's not that bad. So what we need to do is calculate the concentration of all the ions in solution as well as the solution's pH. Okay, so this is a triprotic acid. Okay, so it's got 3 protons that can come off. Okay, so we're going to be finding H+, we're going to be finding H2C6H5O7, we'll be finding minus. We'll be finding HC6H5O7 2 minus. C6H5O7 3 minus, and H3C6H5O7 no charge. Right. 4.
Are you serious?
Yeah. All right, so we want to find out what these concentrations are and what the pH is. Okay. Let me, here I've got, see, some other information we need. Ka1 is 8.4 times 10 to the minus 4. Ka2 is 1.8 times 10 to the negative 5th. And Ka3 is 4 times 10 to the negative 6th. Okay. So the thing to remember with polyprotic acids is that they happen in steps. Okay. You're going to, Ka1 is going to happen. You're going to release the first proton. Okay. Then you're going to take the conjugate base of that. Okay. One negative charge. Okay. It's going to release another proton, according to Ka2. Okay. Then its conjugate base. Okay. The 2 negative charge. It's going to release the third proton, according to Ka3. Okay. And finally, you'll end up with your last conjugate base with no protons left. No acidic protons. Okay? So to do it step by step. Okay? So essentially, something like this, you're going to end up with 3 ice tables. Okay? All right, so if we were to start off with this, okay? Initially, I have just my acid in there, okay? H3C6H5O7. Okay? So we're going to start, we're going to make it a new ice table. What's going to be my reaction? Okay, start with my acid. H3C6H5O7. Single arrow, double arrow. Double arrow. Is that one of your 6 strong acids? No. Okay, double arrow. All right, and so what am I going to be producing? An H plus. And our H2, C6, H5, O7 minus. Okay? So initially, what's my concentration of my acid?
0.7.
0.7. Okay, what about my H plus? 0. None of it's been produced yet. What about my conjugate base? Also 0. Okay, so we're going to get plus X, plus X. You guys are kind of used to this now. 0.7 minus X, X, X. What do I do now? Which Ka? I got 3. Use the first Ka. Ka1. So 8.4 times 10 to the negative 4. I want you guys to notice real quick. Look at the exponents. We're going negative 4, negative 5, negative 6. So what's that tell you about these Kas? They're getting smaller. So what's happening to the strength of these acids? They get weaker and weaker. Okay? So the first one's going to give off the most protons. Then the second one, and the third one will release the least amount of protons. Okay? Alright, so we know how to set this up. X squared over 0.7 minus X. Alright, if I were to plug that in, solve for X, you can either you can ignore X, should be able to with this one. Okay, so what do we get for our value of X? What is it? 0.024. Okay? So, right there, that X, that's going to be our concentration of H plus. Okay? There's going to be some H plus that's going to be added on from the other ones, so we'll see how much that is. Okay? That's also going to be this one down here. Okay? And what's going to be, how much of my acid's left over? 0.024, subtract that from 0.7. What is it? 7.6? Okay. That is right here. 0.7 minus X.
Where'd you get the second one?
This one, that's X.
Oh, okay. Okay.
Okay? Alright, so now we're done with this one. Okay, we can lock that one in. It is done. Okay? What's going to be my next isotable? This one? What's going to be my reaction? Okay, so I'm going to take the conjugate base that we created. Okay, remember, it's still got 2 acidic protons that it can give up. Okay, so that's going to be our acid this time. So I'm using this guy again. H2, C6, H5, O7 minus, remember, double arrow. Okay, Okay, and I'm going to be reforming H plus again. And now I'm making HC6H5O7 2 minus. All right, I'm going to get rid of this stuff down here now. Okay, what's going to be my initial concentration here? What's that? Right. We're going to take the one that we made, okay, so 0.024 molar. That's going to be our initial in our second ice table. Okay, what about my H plus? We made some of that before as well, so that's also going to go in there. Okay, what about this one? 0, right? We haven't made any of that yet.
If we had a problem like this, would they give us like the H plus, the H2? Would they give us all those, or do we have to know how to figure that out?
That I can tell you. I don't know. You know, my best guess is, what I would say is if he only gave you this, he's asking you to calculate the concentration of all the species in solution. From the number of Ka values he gives you, you can tell there's going to be 3 protons that need to be removed. Okay, so you can just take off 1 proton for each one. Okay. Another thing, if you're confused about if it's an acid or base or whatever, notice we have H3C6H5O7. Okay, the hydrogens are split up. Okay, they do that a lot of times with acids so that you can tell which protons are the acidic protons and which ones are just hanging out. Okay, so here we've got 5 of them that are just hanging out. Okay, usually the acidic protons are written out front. Okay, unless like the ones we saw before where you had like the COOH. Okay, there's a few other ones where it's written, it's just, majority of the time you'll see the acidic protons written in the front. Okay, that just might be another way to help you navigate, okay, what am I trying to do here? Okay, so let's come back to this. What's my change? Okay, just like we had before, minus x, plus x, plus x. So we get x, 0.024 plus x, 0.024 minus x. And now what do we do? Plug it all into Ka2. Okay, 1.8 times 10 to the negative 5th. Okay, so now we've got 2 x's to ignore, right? We've got the plus x on top, and then we've got the minus x on the bottom. Okay, so if we do that, what's the x value here?
Ka2.
Ka2?
Because you can cancel out the 0.024s.
Okay. So if we ignore the plus x minus x, okay, you're going to have 0.024 x over 0.024. So like she said, those two are going to cancel each other out, and you're going to be left with just x is equal to 1.8 times 10 to the negative 5th. Does that pass our 5% rule? Is this less than 5% of 0.024? Yeah. Okay, so you can make the assumption to get rid of the plus and minus x. Okay. So now, should we change the H plus concentration? Are we adding that much extra H plus to it? No. Okay, so it's pretty much going to be 0.024. Same thing with this one. We're not really taking away very much of this guy. Okay, so it's going to remain 0.024. Okay, but now we have this one, 1.8 0.8 times 10 to the negative 5 molar. Okay, we're getting there. Okay, we got one more to do. Okay, let's see. Get rid of that. Minus 2 minus. And okay, and we're going to set it up basically the exact same way, right? We're going to plug in those concentrations again. So this one's going to be 1.8 times 10 to the negative 5. What's my H plus concentration? 0.024. What about my last guy over there? 0. We haven't made any yet. Question.
But why wouldn't the H plus value change? Because it would be the value that we would get from the second, doing like the second X chart, it would be like 0.024 plus X. Why would we use that value instead of that?
It really is changing, right? But if you look at it, 1.8 times 10 to the minus 5, right? That's
I can actually tell you what it becomes if you want to write it down.
sure.
It's 0.024018.
Okay.
I don't know if that
So
will help.
0.024, you said 0.18.
Yeah, so that'll.
Okay, so you're not changing it by that much. Right? If you're to calculate pH using this one, the first one, and pH using the second one, pH isn't really going to change there. This is the dominant factor. Okay. All right, and again, we know how to do this. We got minus x, 0.024, plus x. X, am I going to be able to ignore my minus x plus x? Yes. Okay. And so then that's going to give me 0.024 times x over 1.8 times 10 to the minus 5. And that's all going to be equal to 4 times 10 to the minus 6. Okay, so if we solve for x here, what do we end up with? The negative what? 9. Okay, so that's going to be our last one over here. Okay, and so what's my pH of the solution? Like 2 or 3 or something like that. Negative log 0.024. 1.6.
So you can find the pH, I mean, the first.
Yeah.
Basically.
Yeah, because Ka2, Ka3, they're not giving you that many extra protons.
Will there ever be a situation where they won't?
Only if the Ka values are that close. I mean, like here we're getting orders of magnitude different. Okay, but maybe if it was still times 10 to the negative 4. It might. Okay, does that help you with the polyprotic stuff? Okay, it just polyprotic. It's not difficult. It's just time consuming, right? But now you at least have seen one. You know kind of what to expect. Okay. How are we doing on time here? All right. So technically, we got about 5 minutes left. I know we haven't gone over KSP stuff yet.
Could we do a common ion example?
Sure. I've got a common ion one that goes into pH as well. Yeah. That's nice. I like that. That's cute. Okay, so real quick, we'll do this one. Okay, this one's asking you to estimate the solubility of zinc hydroxide. Okay, so we have Zn OH2. Okay. Estimate the solubility in pure water at 25 degrees Celsius. Okay, then compare it to the solubility of the same compound in water buffered at pH of 6. Okay, so we want solubility in pure H2O, and we want solubility in a buffer pH of 6. Okay. So first of all, KSP. What's going to be the formula we're worried about here? What's my chemical equation? What's happening here? What's the SP stand for? I heard someone say it. The solubility product. Okay, so basically we're talking about how much of the zinc hydroxide breaks up and goes into the solution. Okay, so that's our equation. We're looking at Zn OH2. This is the solid. This is single arrow. Or actually, I'm sorry, this is double arrow. And so we are forming the ion Zn2 plus, and we have 2 OH minuses. Okay. So if we look at this, I'll tell you guys the KSP for this is 4.5 times 10 to the negative 17. Okay, so is this a very soluble sample? No, 10 to the minus 17. The vast majority of this is remaining as solid zinc hydroxide. Okay? And what's going to be my formula for calculating KSP? What's my mass action expression here?
Concentration of the products.
Okay, so tell me out.
So concentration of Zn2 plus times concentration of 2OH minus.
Or OH minus.
70% of the way there.
Square.
Right. Okay, and OH minus squared because of the coefficient there. Okay, so what we're going to do is we're going to say let S is going to be the solubility here. Okay, let S equal the concentration of the Zn2 plus. Okay, so if that's the case, what's my concentration of OH minus? What's that?
2S.
It's going to be 2S. Okay, just from stoichiometry, we get 2 hydroxides for every zinc. Okay, so we've got that there. So I can plug that back into my KSP expression. 4.5 times 10 to the minus 17 is equal to, we said, zinc times hydroxide squared. So that's going to be S times 2S squared, right? And that, of course, just breaks down into 4S cubed.
Where did the 2S come
That's, we made the assumption here.
from? Oh, okay.
Okay? Okay, it's cubed, but that's a piece of cake to get rid of here. If we do this and solve for S, what does S equal? I'll just tell you. 2.2 times 10 to the minus 6. And this is moles per liter. Okay? Solubility, usually we're talking about grams per liter. Okay? So how are we going to convert from molarity into grams per liter? You got to use the molar mass. Okay? So I'll just tell you over here, molecular weight is 99.4 grams per mole. Okay? So just plugging that in, 2.2 times 10 to the negative 6 moles per liter. And then taking that times 99.4 grams per mole. And we end up with 2.2 times 10 to the minus 4 grams per liter. Okay, so we're talking about in just pure water, that's in 1 liter of pure water, we can only dissolve 2.2 times 10 to the minus 4 grams of zinc hydroxide. Okay. So now we want to also calculate the solubility in a solution where pH is equal to 6. Okay, so just throw some stuff out here. Do you think solubility is going to stay the same, increase, decrease? What do you think is going to happen? Remember, this is common ion effect. Any ideas? All right, well, let's take a look. All right, do we have all this? Can I get rid of this? Okay, so if we're in pH of 6, we know, what's my pH? 6. It's going to be 8, right? 14 minus 6 is going to be 8. Okay, so therefore, the concentration of OH minus in this solution is 10 to the minus 8. Okay, molar. Okay, so far so good? All right, so if we, again, plug in, assuming S is equal to the concentration of Zn2 plus, okay, we have the concentration of OH minus. Okay, the major contributor is going to be the buffer solution. Okay, you saw how much OH minus was being produced with just the pure zinc hydroxide. Okay, so here, if we plug this all in, so that's going to be equal to KSP over OH minus, just rearranging that equation. Okay, and so we had, again, 4.5 times 10 to the minus 17 over concentration of hydroxide. But remember from our equation that this is squared. Got that? Okay. And so if we do that, we end up with 0.45 molar. Okay. And if we were just to go ahead and convert that back, 99.4 grams per mole, comes out to be 43 Okay, so we've drastically increased the amount of the zinc hydroxide that can be absorbed or dissolved in the solution. Okay. And so if we were to go in and talk about like the common ion effect here, okay? You know, one way you can think about this, and what I think is the easier way, is, you know, we're starting at a pH of 6, all right? So is there more H plus or OH minus in the solution? More H plus, okay? So I'm putting in zinc hydroxide, right? Okay? So when I put in that zinc hydroxide, you know, there's going to be H plus in there already, right? So if I have H plus and OH minus in there, what's going to happen? What? Well, what happens when you put H plus and OH minus together? They make water, right? So those are going to come out as water. What's going to happen to my equilibrium? It's going to shift to the right, right? Because we've used up the OH minus. Okay, so that's going to shift this way to produce more OH minus, dissolving more of that zinc hydroxide. Okay, so you know the common ion effect works very much the same way. You know, you're basically looking at what do you have in your solution already, what are you putting in, okay, and how is that going to be affecting the direction? Think Le Chatelier's principle, right? You guys did that in equilibrium.
How does it shift to the right again?
Because here we've got this competing reaction. Okay, H plus is reacting with the OH minus. Okay, so essentially we're taking OH minus out. Okay, so we got shift right.
Why here did you say S equals concentration of zinc equals KSP over OH minus squared? Why did you?
It was just rearranging, right? Because KSP is zinc times OH minus squared. So I just rearranged to solve just for the zinc. Okay. Any other last questions before we go? All right. Best of luck to you guys. Study hard. If you have other questions, you can stop by the ARC. Not right now.
What are your hours of art?
Let's see. Tomorrow I'm there. What time am I there? Did everyone sign in on the sheet? If you haven't signed in on the sheet, please do so. Thanks for coming. I hope I helped.
Do you want me to send your hours to the box? Could you maybe send your hours to Dr. and ask him to send us all this?
Sure.